Hey everyone, welcome to another episode of Data Structures and Algorithms. In this episode, we are going to talk about time complexity. What is big O? Big O notation describes the time complexity, how fast an algorithm runs, and space complexity, how much memory it uses in the worst case scenario. It helps us analyze how an algorithm's performance scales as the input size grows. So, here are some examples for big O. So when considering big O, there are some key points we should know. So one is that the big O notation is a mathematical representation of an algorithm's efficiency. It focuses on how runtime grows relative to the input size. Let's take like n. N is like a variable x that that we use to make sums in maths. So the other thing is that we ignore constants and lower order terms because in the grand scheme of things this minor ones doesn't really matter. So imagine I'm doing a task that takes n plus 1 amount of time. We just take it as n because the plus 1 doesn't really matter in it. So here for an example, I have a function called add. In this, it takes an argument, any argument that we give. So the for loop iterates over the number of over any number of n, and then I to sum, and then it returns the sum. Like imagine we are giving argument n is equal to a million. So in this case, it takes about a million steps because this has a run time of on linear time. In this, the with the size input size, the time grows proportionally or linearly. So I'm going to do this the same function. I can write the same function in another, which is sum is equal to n multiplied by n plus 1 divided by 2, and then return star. In this, we are also giving an input as a million. So in this, it takes only 3 steps. It takes only 3 steps. This has a runtime of O1 constant time. So even though it takes 3 steps, we don't write 3 over here because like in the grand scheme of things, the minor steps don't really matter. So we just take it as 1. So when we consider both of them, this is way better than this. So the constant time is way efficient and faster than the linear time. So yeah. So here's a graph I made up. So the x-axis consists the input size or the n or data, and the y-axis has the operations or the time. So here's a quick breakdown of the most common time complexities that you'll encounter. So the first one is O1, which is the constant time. In this, think of an array axis. It's like super fast. So like another example for it is inserting at the beginning of a linked list. It's just way faster, even though even with this number, when the number of size inputs increases, it's still it takes the same amount of time. So the next one is log n, which is logarithmic time. This means that the running time of an algorithm is proportional to the algorithm of the input size. So just imagine binary search. It's like where you slice a problem in half each time. So the next one is ON, which is the linear time. The running of an algorithm grows linearly with the size of the input, just like one step per item. If you are taking considering a loop, considering a series of steps, it just follows one step at a time. It's like that. So like the next one is quasi-linear time, which is n log n. So in the quasi-linear time, it's like, for example, it's like the merge sort or the quick sort. It's better than the quadratic, but not the best because it takes a lot of time and a lot of steps to complete. So the next one is the quadratic time, which is o x o n squared or o x squared. In this, the running time of an algorithm is proportional to the square of the input size. So imagine nested loops. It's just, you should watch out for it because the performance drops fast. So the worst or the most slow or the slow that are painfully slow are exponential time and factorial time. Exponential time is the running of an algorithm doubles with each addition to the input data set. So, for example, I can see this is the Tower of Hanoi or the recursive Fibonacci. It's like very slow because it takes a lot of time and a lot of steps. And factorial time is that the running time of an algorithm grows factorially with the size of the input. This is often seen in algorithms that generate all permutations of a set of data. It's like the worst or the slowest thing you can use, so it's mainly used for brute force permutations. So why does Big O matter? The Big O helps us to choose the best algorithm for large scale data. Just imagine the real world impact. In the real world, we use Google search, right? For Google search, it should be able to handle 1 billion of queries efficiently. So, and another example is database indexing. Imagine we have a large database that we have to look data very fast. So in this, for this we have to choose a good the best algorithm that we can use for database indexing. And the next one is another example is game development. In this we can optimize collision detection, things like that. So I'll ask you a quick question, and the question is, would you prefer an ON or ON squared algorithm for sorting 1 million records? To summarize this, Big O measures scalability, like ON and O log n are excellent, by ON squared and the exponential time should be avoided for large inputs.